and welcome to today's The Bridge Show. And what a show we have for you today. You know, we had a lot of fun the last weeks with, the Halloween show last week was absolutely hilarious. Even I actually got to laugh a lot on that one. But today we are going deep dive into the technical nitty-gritty of the VB440. So welcome to the show. And of course, welcome. And welcome, Kenneth.
Oh, thank you, Simen.
It's so good to have you here. We've been, I've been trying to get you on the show for many weeks, actually, but yes. We finally succeeded. And I know that you're very happy to be here.
Yeah, I'm extremely happy to be
I know that you're lying through your teeth.
Oh, yes.
But that's kind of fine. That's okay. For those of you that don't know Kenneth is one of our senior developers. He's have contributed tremendously to the VB440, and he's also responsible for the amazing user interface on the 440. And it's the 440 we're going to talk about today because we've been covering it in general terms, and we released the new instrument U kits on the iPad and blah blah blah. But let's go crazy about some of the inner analytics, and we have some help as well. We have actually Marcus. Hello, Marcus.
Hello.
Cool to have you here. Marcus is going to guide us so that basically Kenneth is now in the driving seat, the red chair driving seat. And
yes, good thing I have a driver's license then.
Yeah, you don't have a driver's license.
No, I did not.
Only for the 440.
Oh, yes.
Well, that's kind of good. So we are actually then going to have a look at some of the features in the 440. And Marcus, take it away. Can you show us the network page, basically, where we actually go into it? Because one thing is the timing aspects. And if you scroll down, you can see that there's a lot of different types of things that you can go bananas with. But I really want to go one back, can you show us, Marcus, the capture page, because that's one of my favorites. It's kind of boring. It's just a page, but that means that you can do actually PCAP captures of any kind of stream and flow. You can actually then decide what basically parts of the service that you want to capture. You can capture absolutely all the flows if you like. And you can then set, of course, the capture length, and it's as easy as just hitting capture, and then basically you have a PCAP. There you go. Do we have a packet capture program on this machine? Try it and see. Just hit the PCAP link, Marcus, and see how it goes. Yes, we do. We have Wireshark, basically, so just hit there we go. So, is this easy or is this easy? This is easy.
It's extremely easy and convenient. So, when we launched our packet capture capability, we had customers who were actually struggling to do this simple operation of just capturing some packets and analyzing them offline.
Yeah, because it's not easy. The normal PC doesn't come with a 100 gig interface,
It does not.
So you kind of need a lot of bandwidth, and you need, of course, the accuracy as well, which is also very nice. And I know that we also have now included the ability to do PTP packet capture, so that you can actually analyze a lot of the timing information. Yes.
So turns out that the PTP traffic, that is the let's say timing and synchronization element in a 2110 setup, is pretty much intrinsically related to your audio and video streams. Yeah. So now we include all the PTP signaling traffic that the probe or the 440 receives together with your stream captures by default. Yeah, so if you're diagnosing a problem in the field, you get this PTP traffic together with your audio, video, and/or ancillary streams. So that if the problem that is manifesting itself is related to the PTP timing, you have a better chance of
finding it,
of capturing that problem. Yes.
Because also one other thing is that we now have also the rolling capture capability. So it's a ring buffer that basically then always captures.
Yes. So it turns out it's also usually very difficult for customers to capture all their traffic on a 100 gigabit interface over any significant amount of time, really. So in the 440 now, we have a rolling capture feature, which means that you start your capture, but you don't really have a end time or end date. It keeps capturing, and then when it reaches a certain limit, which you specify, it will delete, it will push out the earliest data.
So it's then a rolling window of capture?
Yes, exactly. Yeah. So this allows you to, for example, say I want the last 10 seconds of all the video traffic for streams X.
And it will then just have 10 seconds of the last, and when you hit save, then basically you keep that.
Yes, you get those 10 seconds. So if there's something that you just realize a couple seconds later that you really wanted to capture, you can have that capture.
That's extremely valuable, I must say.
Yes.
We use that ourselves, and we have some very, very nice customers out there, which believe me, has thanked us for that feature, but I love that feature. That's very, very good. But let's go forward to the timing, because one thing is going into Wireshark, which of course is, you can go as deep as you like.
That's really low-level stuff.
That's the low-level stuff, and that's not for the faint of heart.
No.
you need to understand what you're doing, actually. But let's go into the specifics that we provide, because we have then, on top of here, we have the path delay, which is basically then the ability to show the time difference between the sender and us as a receiver.
Yes, when we receive the packet. So it's actually timestamp of the packet versus the time we receive it.
Yeah.
So a path delay, for example, can never be a negative value.
No.
Because that will mean we actually receive it before it's supposed to be.
We'll go back into the future.
Exactly.
Yeah.
So right now, with the physical laws we know of, that's really not something that's possible. So a negative value would immediately be an error.
Yeah.
But of course, arbitrary large values are possible, depending on your network topology.
Yeah, because if you're using this, like some of our friends in NAP, which then have a lot of remote production, and then going into the hub, you will of course have quite a significant path delay, because the network introduces.
Not to mention potential multi-continental.
Exactly.
Atlantic crossing type.
It's still,
scenarios.
kind of 70 milliseconds of physicality between us and America.
Yes. So in our lab here, we don't really get any significant propagation delay in our network.
Which we can see actually after diagram, because how much path delay is it on the video on this one, Marcus?
I would believe it's around somewhere around 700 microseconds.
Yeah. Well, that's
for the video stream.
Yeah.
So it's a complicated reason why, but the timestamp doesn't necessarily reflect the exact timestamp that the first packet was sent. And the reason for this is more complicated and has to do with, let's say, SDI signals.
Yeah.
So in SDI, you will have something called blanking.
Yeah.
And the blanking interval isn't transmitted as packets in a 2110 system, because for the video stream itself, you only transfer the pixels, as
the
it may,
physical
or
pixels from
what was called the raster of the video images. So the blanking is left out from the transmission, but the let's say sampling instant or timestamp still reflects the start of the video frame as if it had a blanking interval. But well, I should clarify that this is for a narrow
transmitter, of course. Yes.
So you also have something called a narrow linear transmitter, which doesn't have blanking, which does not have the extra blanking interval inside the
I get it. But you know, this
This is complicated stuff.
This is very complicated, but I love to talk about it. And one of the design goals of especially the timing interface here was to give insight into a lot of this. And you know, let's jump to the next one, which is basically the RTP align.
Yes.
And the RTP align is again pretty significant because, arrest me if I'm wrong here, it has to do with the ability to synchronize multiple devices and be sure that basically they are aligned and that there's no kind of the, let's say, synchronization by the first kind of, or the timing information. I'm just blabbering now. Please correct me with what's actually correct here.
Yeah, so whenever you have 2 or more cameras, you will ideally have a way to frame synchronize them.
Yeah. Like in the old days, like with Blackburst.
Yes. So we try to avoid these analog extra cabling that a Blackburst setup would require. So in a given 2110 system, you have a certain prevailing frame rate, and each frame has really a given point in time where the cameras should perform their image acquisition.
Yeah.
So which we would call alignment points. So it's really given that any camera that derives its timing and synchronization from a PTP network and is 2110 compatible.
Yep.
Should be acquiring or sampling the images at a given...
the same rate, basically.
Yes.
Yeah.
And at a given point in time. So the RTP alignment offset is telling us how far off the timestamps that the camera is using is from the alignment points.
So it's actually then taking the first pixel on the frame and actually then measuring that against the PTP alignment?
Yes, the timestamp from the video frame that's received from the network.
What does the alignment say here, Marcus?
No, it seems fine.
Yeah, it's in fine. It's at
and by fine, it means it's 0. Yes,
yeah.
So it's perfect.
It's
so
perfect.
If your alignment point is offset by any meaningful value, you have a camera which is not timestamping at the correct point in time.
So that means that basically it will then start capturing, into the pixel grid differently than the other cameras.
Yes, so that will mean the camera isn't synchronized as it should in a 2110 system.
Well, that's understandable. I think that, anything else but 0 is bad.
Yes, so this also applies to SDI or 2022-6 sender if it's compliant with this something called 2022-8, which is really retrofitting the 2110
with the blanking
back
and
into
all the which we love to get rid of. Please get rid of blanking. We don't like it. Even though I'm an analog guy from a long time, I love to see that gone. So that's fine. But we have more. We have also the first packet time, basically, which is significant. So what's first packet is obviously the first packet in the frame, right?
Yes, it's the timestamp we receive the first packet of each frame.
And what does that graph actually signify? Because I can see the first packet time being it's very flat.
So it's showing us. So if we just show you the time, that will be just a graph that just go upwards, right? Or whatever.
Of course.
Yes. So this is of course relative to something.
Yeah.
So this is relative to the. So this is the timestamp of the frame relative to the. What is it? Relative to the.
To the physical frame rate, the physicality of the
alignment points, I believe.
Okay. So basically, it's the first packet of an aligned frame. That's what it actually signifies.
Yeah.
I'm being too. I'm not being accurately enough for you here, I guess.
Well, it's a lot. It's a mouthful to take in all these concepts.
Well, it's nice. Let's just move to the first packet margin then, because that's different from
so that's,
the first packet.
Sort of like a derived value
Yeah.
from the first packet times.
And where is that? Is that graph number 4?
Yes, it's the graph immediately below the first packet time.
Yeah, where is it, Marcus? There you go. Yeah, there it is. Oh, thank you.
So the first packet time margin is a more, I'd say, easier value because it's relative to 0, really. So I was talking about this blanking periods.
Yeah.
So the blanking isn't sent in a 2110-20 video stream.
No.
So we sort of have this, let's say, pre-calculated value of how long the blanking interval would be for a certain video frame size.
It's typically the time between frames.
Yes. So this value can be pre-calculated.
Yep.
And we do that, and we add some let's say. Padding or margins around that, and we say that we expect to receive a packet, well, the first packet, start of
a physical frame.
The first packet of a frame at a certain point in time after the alignment point.
Yeah.
And we call that the transmission offset or TR offset. So the first packet time margin is telling you how much margin in time that was available between when we received the first packet and the TR offset.
Marcus, while we are at it, show it, because you're showing these graphs basically now in the 30-second interval. Can you show them, with a bit faster refresh? Go to the 5. There you go. Yeah. So this is actually then 5 seconds of what we're looking at. And when you talk about the first packet time and the first packet time margin, what kind of measurement units are we using here? Because this is obviously not seconds, because it's frames. Basically, it's obviously not milliseconds, because that's not good enough. So what is it?
So it adapts that dynamically, but right now I believe the graph is showing microseconds.
Yeah.
So it's in that range, microseconds. So the margin has to be above 0.
Yeah.
If it's below 0, you received something before you were supposed to receive it. It can't be too large, because then you have there will be there's a certain requirement, a buffer requirement in the receivers.
Yeah.
So if you receive something way too early or too late, you would
of course
either
it's outside
exceed
of the
or
ability to buffer. What's
yes,
the typical buffer size in a narrow type of signal? Is it been 40?
It's around, I believe, 8 packets.
Okay, exactly. So it's very, very, very small.
Yeah. So there's something called a narrow receiver and a wide receiver.
Yeah, but because that actually brings me to the next kind of thing. And Marcus, if you can show us, because you have then the virtual buffer. If you scroll a bit down there, you have then actually the VRX. And tell me, because we're now into the differences between the narrow receivers, wide receivers, transmitters, and of course wide and narrow, which basically, just to confuse everybody, is interesting. But the VRX is very useful in determining what type of transmitter this is, right?
Yes, or yes. So whether it's compliant to a narrow or a wide profile is really why this VRX model was developed.
But what's the tree graphs? Because one thing is that the virtual buffer, then you have underflow and overflow.
Yes, perhaps I should explain that in a 2110 system, you either have all your receivers are either narrow or wide.
Yeah.
If you ever have let's say a wide transmitter in your network, you should really also have receivers which support a wide.
Yeah, because if you're, as you say, in a narrow system, you have 8 packets of buffer, and that's
it's really nothing.
That's
It's
really nothing.
Just a few lines of video data or
Exactly.
pixels, really.
But that means that if you then have a wide transmitter, that can be multiple frames or more.
Well, it can't really be multiple frames of jitter, but it's a lot more than a narrow transmitter. So if you have a very stringent receiver, which only supports narrow streams, it can't receive wide transmitter streams. So in any network, if you have one or more wide transmitters, you really want all your receivers to be capable of receiving wide streams.
Well, so basically, again, it's a useful tool to be able to determine what type of signal.
Yes. So this first graph in the VRX group here is telling you really how many packets you would need to buffer.
Yeah.
So it's for a narrow receiver, this value is somewhere between 0 and 8.
Yeah. What's the value right here, Marcus?
For a 1080 video.
Which is the value? I can't see it because it's too far from me, so you have to tell me.
It's about 5.
Yeah, that's
It's about 5. That
pretty
sounds
good.
about great.
As long as it's not over 8, basically, or something. Then,
yes,
then
for
you're
a
fine.
higher definition stream, let's say 8K stream even, you will have some bigger allowances in the buffer, but it's really just a few packets.
Yeah.
So compared to a wide receiver, which would allow up to, well, in this case, up to around 720 packets. There's a big difference in the amount of packets that the receiver will have to buffer or support buffering.
But I get it, I get it.
Yes,
I hope
it's
that
really good.
basically everybody out there as well is getting it. You're getting it, I hope, because,
Yes, so to be able to really gauge how many packets are received too late or too fast, you have this underflow and overflow values. So in our lab here, those graphs are both 0, which is what you should hope they should be.
That's good. 0 is
Because
good.
if you have this underflow or overflow, that really means that the packets were received either too early or too late.
Yeah. It's just, it's just giving you the virtual receiver what's actually going on the receive side.
So when you're, let's say, combining several cameras, or like in a switcher, if packets are received too late or too early even, that will cause problems for your production, really.
Well, of course, and then that's the beauty of these simple diagrams that basically then enables you to understand immediately what's going on. But I want to come to the last kind of graph that we have here, and that is, the C factor. What's the C factor?
The C factor.
Yes, what is the C factor?
I'm glad you asked,
Thank
Simen.
you, yes.
So this really tells you how bursty the transmitter is in how it paces out packets in the network. So the reason this is interesting is that we're dealing with pretty high bitrate streams here. Yeah. So to be able to utilize your network resources optimally, let's say you have a 100 gigabit link, to be able to utilize as many of those gigabits as possible, it's necessary for all the streams within that link to transmit their packets as let's say evenly and nice as possible. Exactly. So if you compare this to like a real life traffic situation, if all the cars just drive evenly at the same pace, you'll have a nice moving flow of traffic. Whilst if some cars are just stepping it on the gas pedal and racing, and others and then braking, you're gonna have a lot.
It will be congestion, and it will form queues, of course.
It will form queues, but they also might lead to some let's say, traffic incidents and lost cars or packets in this scenario. So you really want to have
Not a lot of burstiness.
Not a lot of burstiness. So the
Because
C-value
burstiness,
is...
and just to clarify here, because
Yeah.
burstiness is not the same as jitter, right? So you have then jitter, which is caused by the network forwarding, or you have then burstiness, which is actually caused by the transmitter.
Yes. So jitter might occur because you have queuing and burstiness to begin with. So this is more like a trying to diagnose or the problem with the, let's say, easiest way possible.
Yeah. Well, but guys, I hope that your brains are still working after this deep dive into some of the technical aspects. But thanks for basically thanks to our cultural alibi, our mad musical genius. He's here today with some really, really nice Norwegian music, just to cool you down after this dramatic influx of brainiac stuff. So let's go to our mad musical genius. Well, thank you, Axel, and it's always good to finish on a cultural note after this influx of highly detailed explanations. Thank you very much, Kenneth. I really appreciate taking the time to be with us today. And of course, to everybody out there, if you want more information about this, please contact your local representative or contact us and go crazy. Of course, there's always the demonstrational system you can go around and play with as well. And please don't forget to subscribe to this channel. And that is everything. So it's over and out from the Oslo IP studio here at the Bridge headquarters in Oslo. Have a great week, folks.